In this video, we're going to get a little bit of practice with finding a Maclaurin series and using a Maclaurin series to help approximate the value of a function. So here's the question we want to address. Find the Maclaurin series for sine x and use the third degree polynomial to approximate the sine of point 1. How accurate is your approximation? So you may remember the Maclaurin series for sine x, the power series for sine x. But in case you don't, or if you want a little bit of practice finding a Maclaurin series from scratch, let's go ahead and figure that out from scratch. So here's the formula for a series. In order to find a Maclaurin series, you need to evaluate your function and all its derivatives at the value 0. We need f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus the third derivative at 0, x cubed over 3 factorial. And we keep going. We need every derivative evaluated at 0 times x to the n over n factorial. So the first step is to find all the derivatives of sine and evaluate those derivatives at 0, and hopefully we'll be able to see a pattern that will enable us to find the series. Let's make a little bit of room and let's get started. So f of x is equal to sine x. F of 0 is 0. The first derivative of sine x is cos x, and cosine of 0 is 1. The second derivative, the derivative of cos x is negative sine x, and evaluating that second derivative at 0, the sine of 0 is 0. That is correct. Now we take the next derivative, third derivative. That's the derivative of negative sine x. That would be negative cos x. And evaluate that at 0. Cosine of 0 is 1, but we have a negative in the front, so that's a negative 1. Let's do one more derivative, and I think we'll be able to see a pattern. When we get beyond 3, the convention is to put the number 4 up there as a superscript in parentheses rather than many, many, many little apostrophes. The fourth derivative is the derivative of negative cosine, which would be a positive sine x. And again, evaluating that at 0 is 0. And I think we can already see a pattern happening here. Every other derivative will be 0, and the non-zeros will alternate between 1 and negative 1, 1 and negative 1, 1 and negative 1. So plugging this into the formula for the series, we get that our series is equal to, first term is actually 0, second term just plain old x. Third term is the derivative, the second derivative, which is 0, and just for completeness, let's put this in so we see where it's coming from, x squared over 2 factorial. The next one is a minus 1, x cubed over 3 factorial. Next one is a 0, x to the 4th over 4 factorial, plus 1, x to the 5 over 5 factorial, etc. Every other term is 0, so we can write this a little more neatly as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial, etc. Now we can use that series, but only up to the x cubed term to approximate the sine of point 1. So we want to use Let's call this P3 of x for the third degree polynomial, x minus x cubed over 3 factorial. And we plug in a 0.1. 0.1 minus 0.1 cubed, 3 factorial is 6. 0.1 cubed over 6, which is 0.1 minus 0.001 over 6, which is approximately 0.0998. That's our approximation for sine of 0.1. And now the question is, how accurate is that approximation? You may punch that right into your calculator and say, well, what is the sine of 0.1 on my calculator? And on your calculator, the sine of 0.1 should come out to be, go ahead, try it. Did you get this? 0.998334166. Pretty close, right? But let's use Taylor's theorem to see how accurate that approximation is. Let's just note this. This is what we got on the calculator. All right, Taylor's theorem says that the remainder can be given by the fourth derivative, because we went up to the third degree, at z, we'll talk about what z is in a second, times x to the fourth over 4 factorial. Now this x is the x that we're plugging in. That's exactly the 0.1. But what's the z? The z is some number between 0, because that's where our Maclaurin series is always centered, between 0 and the x that we're interested in this case, 0.1. We don't know what that number is, but maybe we can see how bad that number could possibly be. So we'd like to try to find the worst case for that fourth derivative between 0 and 0.1. So first of all, let's remember what the fourth derivative was. And remember, we started with sine x. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. And the derivative of negative cosine brings us right back to sine. So the fourth derivative is sine x. We want the worst case of sine x, and that means the largest possible value for x's between 0 and 0.1. And there are two ways to think about this. One thing to think about is that sine x is an increasing function from 0 up to pi over 2. Pi over 2 is about 1.57. So the worst case that sine x could be is sine of 0.1. But we still don't know how much sine of 0.1 is. That was the whole point of this exercise, was to approximate the sine of 0.1. So the other approach is that we know the worst case sine can ever be is 1, right? Because the sine function has a range from -1 to 1. So the worst case is really 1. So let's just use 1 as the worst case. So the error is not exactly equal to, but it's certainly bounded by, it's less than or equal to 1 times 0.1 to the fourth, 1 times 0.1 to the fourth over 4 factorial, which is 0.10001 over 24, or approximately 0.000004. Now that is a tiny error.